Any serious discussion of mass spec has to include a discussion of isotopes. So isotopes, as you might recall from general chemistry, are structures that have the same atomic number but a different atomic mass. How does that happen? Well, that's due to a different number of neutrons in the nucleus. The number of protons in the nucleus is what makes an element an element. You know, a carbon is a carbon because it has 6 protons in the nucleus. If it has 6 neutrons also, it's going to be carbon 12. But if it has 7 neutrons, it's going to be carbon 13. If it has 8 neutrons, it's going to be carbon 14. And the fact that a neutron has a mass similar to that of a proton means that if you have more neutrons in the nucleus, a molecule containing an atom of a heavy isotope will show up as having a different mass in the mass spectrum. Okay, so what we're going to be primarily referring to today are what we call stable isotopes. Now, everybody has heard of radioactive isotopes, and in fact, that's what most people think of when they think of the word isotope. Examples of radioactive isotopes would be carbon-14, tritium, phosphorus-32, uranium-238, etc. Those are unstable nuclei that over some length of time will decay. In the process of decaying, they give off high-energy particles, and they're generally bad for you. If you work with radioactive isotopes, you have to take some sort of precaution not to expose your body to the radiation that's being given off. Stable isotopes are a completely different ballgame. They are completely stable. They don't decompose. If you have a molecule with an atom of carbon-13, it will always be a molecule with an atom of carbon-13 in it. It just so happens that a small amount of the carbon can have an extra neutron in it, and similarly, a small amount of hydrogen can have an extra neutron. Okay, so if a hydrogen has a neutron, it's called deuterium, or 2H. If a carbon has an extra neutron, it's called carbon-13. Of these two isotopes, carbon-13 is the more important one because it has a greater natural abundance. So 1.1% of all the carbon in the world is carbon-13, but only 0.02% of the hydrogen is deuterium. So what this means is that if a molecule contains a carbon-13 or a deuterium atom in its structure, its mass will be greater by 1 AMU than all of the carbon, than if all of the carbon was carbon-12 and all of the hydrogen was 1H. So this phenomenon frequently gives rise to a small M+1 peak, as we call it, which is a peak that is 1 atomic mass unit higher than the molecular ion. Okay, let's look at a couple of examples. Decane is 10 carbons, as you should well know. Icosane, which you may not know from the name, is a 20 carbon molecule. So looking at the relative abundance, this is a blow-up of just the molecular ion region of these spectra. Obviously, there are going to be many more fragments, but if we blow up the molecular ion, we see that the M+1 peak for decane is, I don't know, 10, 15% of the size of the molecular ion, and for icosane, it's bigger. It looks like it's about 25% of the size of the molecular ion. So this brings forth the principle that the bigger the molecule, the greater the probability that there will be a carbon-13 somewhere in the molecule. Doesn't matter where it is, as long as it's somewhere. So then there will be a greater intensity for the M+1 peak. In fact, if you got to a molecule that was as big as 50 carbons, given that any particular carbon has a 1% chance of being a carbon-13, once you get up to 50 carbons, you would actually have a 50% chance of having a carbon-13 somewhere in the molecule. So the M+1 peak would then actually be the same size as the molecular ion that you would calculate if everything were carbon-12. By the time you get up to 50 carbons, there's a 50% probability that any particular molecule that you observe, whose ion reaches the detector, has a carbon somewhere with one more neutron. We don't normally look at molecules that are that big, but isotope peaks are present, and they do give you some idea, very, very crude idea, of how big of a molecule you're looking at. The other place in which isotopes are really important is if you have an alkyl halide, or molecule with either chlorine or bromine in it. You see, deuterium and carbon-13 are what we call low abundance stable isotopes. But chlorine and bromine have two high abundance stable isotopes. Chlorine, its atomic mass on the periodic table is 35.45. What that means is that it is a 3-to-1 mixture of chlorine 35 and chlorine 37. So 75% of all the chlorine atoms out there have a mass of chlorine 35, 25% of them have a mass of chlorine 37, meaning that they have 2 additional neutrons in their nucleus. So any compound that contains chlorine will have 2 molecular ions, and those will show up in a 3-to-1 ratio, and they will be separated by 2 atomic mass units. So in this example of chlorobenzene, you get a molecular ion at 112, another molecular ion at 114. Those are appreciable peaks, as you can see, and they are in a 3-to-1 ratio. You do see 2 small peaks at 111 and 113. Those are the M+1 peaks that we talked about on the previous slide. Bromine is a 51-to-49 mixture of bromine 79 and bromine 81. Okay, so compounds that contain bromine will contain 2 molecular ions also, and they will be in approximately a 1-to-1 ratio, and they will also be separated by 2 AMUs. So in this case, bromobenzene, it has a peak at 156 for bromines that have a bromine 79 atom, and 158 if the bromine atom in that molecule happens to be a bromine 81. One more rule that I want to introduce here as we conclude our lessons on mass spec. This actually has nothing to do with isotopes, but I'm just sticking it in here as a final thought, is what I call the nitrogen rule. And that is for molecules that contain just carbon, hydrogen, nitrogen, and oxygen, or any combination. It could be just carbon, hydrogen, and nitrogen, but oxygen doesn't change things. If the molecule has an even number of nitrogens, it will have an even mass. And if the molecule has an odd number of nitrogens, it will have an odd mass. Okay, so you can see these examples of molecules that are similarly sized with 5 non-hydrogen atoms. Pentane, which has 5 carbons, has a mass of 72, which is even. Butylamine, which has 4 carbons and 1 nitrogen, has a mass of 73. It has an odd number of nitrogen, so it has an odd mass. And finally, propylene diamine, which has 2 nitrogens, the mass is now 74, even number of nitrogens, even mass. Okay, so most of what you're going to have to do with mass spec is use the molecular ion to be able to determine what the mass of the molecule is. You will get more structural information out of IR and NMR, but some of these other little tidbits that we've talked about, especially the isotope peaks and the nitrogen rule, could help you figure out what is present in your structure, just based on interpreting the mass spectrum. There are many, many, many more applications of mass spectroscopy in chemistry, but since we are just focusing on small organic molecules, we've dealt with the basics that are relevant to that application. So now in the next lesson, or in the next series of lessons, since it's such a large topic, we will move forward and talk about nuclear magnetic resonance spectroscopy, which is really going to give us the information we need to be able to solve structures.